Good morning, friends. Now, further numerical of the MCQ question asked in JEE exam. Now, the question asked in 2009. Here, when radiation of 400 nanometer wavelength is incident on a photocell, emitter produces the photoelectrons with maximum kinetic energy of 1.68 electron volt. Work function of emitter will be. That means here wavelength lambda is given. Also, the maximum kinetic energy of the photoelectrons emitted is also given. That is the 1.68 electron volt. We have to find out the work function of a given matter. For that purpose, we are using the Einstein's equation. HF is equal to HF0 plus half m, which is the maximum. That means the HF is equal to HF0 plus half m, this square maximum. HF0 is the work function, and here instead of the HF, here the wavelength given, therefore we can write HC upon lambda is equal to 5 plus maximum kinetic energy half m, this square maximum. Now we require this work function, therefore phi is equal to HC upon lambda minus half m, this square maximum. Now we substitute the value. In our question, value of HC is given 1240 electron volt into nanometer. Therefore, phi is equal to 1240 upon lambda. Here, HC is given in nanometer. Therefore, we write the lambda in nanometer. That is the 400 minus maximum kinetic energy is given 1.68 electron volt. So it's equal to 3.1 minus 1.68. That is the 1.42 electron volt. That is the work function of a given matter. Now again, here what is given? When radiation of 400 nanometer wavelength is incident on photocell, emitter produces photoelectrons with maximum kinetic energy 1.68 electron volt. So work function of emitter will be. For that purpose, we are using this relation. HF is equal to HF0 plus half m square maximum. Actually, maximum kinetic energy is equal to HF minus 5. Therefore, HC upon lambda is equal to 5 plus half m square maximum. We require the phi work function. Therefore, phi is equal to HC upon lambda minus half m square maximum. Value of HC is given in electron volt in nanometer 1240 divided by wavelength in nanometer 400 minus maximum kinetic energy is given 1.68 electron volt. Therefore, 3.1 minus 1.68, so 1.42 electron volt is the answer. That is the work function of a emitter for the given matter. After that, next, asked in 2010, from source of power 4 kilowatt, radiation emitted are such that photons are emitted at a rate of 10⁻20 photons per second. That is the N upon T is given. Number of photons per second, 10⁻20. This radiation will be in which region of electromagnetic waves? For that purpose, we have to first find out the either wavelength or the frequency. So we can judge that this radiation lies in which region of electromagnetic spectrum. For that purpose, we know that the power P is equal to total energy upon time, En upon T. But total energy, suppose the n numbers of the photons are emitted, therefore NHF upon T. So here N upon T is given. As we find out the frequency F, therefore F is equal to P upon N upon T into H. Planck's constant. Power is given 4 kilowatt, therefore 4000. N upon T, number of turns, the number of photons per second emitted, 10:20 is given, therefore 10:20. Into Planck's constant 6.62 into 10⁻² minus 34. So we can find out the frequency of this radiation, then 6.06 into 10⁻16 Hz. 10⁻16 Hz. This frequency is of X-ray. This frequency of X-ray region. Therefore, what are the radiation take place in this case that lies in X-ray region? So we can also find out the wavelength from the frequency, because the C is equal to F lambda. Therefore, lambda is equal to C by F. Again, from the source of power 4 kilowatt, radiation emitted are such that the photons are emitted per second is 10⁻20. This radiation will be in this region. So here the power is given, therefore we know that power is equal to energy radiated per unit time, En upon T. In this energy, suppose the n numbers of the photon, and one photon has the energy is hf, therefore total energy is nhf upon T. Now n upon T is given 10⁻20 photon per second. We require the frequency f, therefore f is equal to power upon n upon T into h. Substitute the value, we obtain the frequency is 6.06 into 10⁻16 Hz. So this frequency lies in X-ray region of electromagnetic EM waves of the EM spectrum. After that, the next asked in 2011. So a nucleus of mass capital M is initially at rest. Therefore, initial momentum is 0. It absorbs the neutron having the mass capital Mn, rest mass, compound nucleus divided into nuclei of M1 and pi M1. If wavelength of nucleus with mass M1 is lambda, then wavelength of the mass will be. So we are using the law of conservation of momentum. So here, law of conservation of momentum. Total momentum is 0. Therefore, P is equal to vector P1 plus vector P2 is equal to 0. Therefore, vector P1 is equal to minus vector P2. Considering only magnitude, so what we obtain? P1 is equal to P2. P is equal to h upon lambda 1. Here h upon lambda 2. H is cancelled. Therefore, lambda 1 is equal to lambda 2. Therefore, the wavelength of both mass, either M1 or pi M1, are same. Therefore, lambda 2 is equal to also lambda. Again, a nucleus of mass capital M is initially at rest. Therefore, total momentum is 0 initial. It absorbs the neutron of mass capital Mn having the rest mass compound nucleus. That means this our original nucleus is now divided into the two parts, so the two nuclei of mass M1 and pi M1. If the wavelength of nucleus with mass M1 is lambda, then what is the wavelength of the mass of the other nucleus? So here we know that the law of conservation of momentum, total momentum P is equal to, when the nucleus is divided in two parts, therefore the momentum of first part plus momentum of other nucleus. So P1 plus P2 is equal to 0, therefore P1 is equal to minus P2. Now considering only magnitude, therefore P1 is equal to P2. Now we know that momentum P is equal to h upon lambda. we are using this concept, h upon lambda 1 is equal to h upon lambda 2. So h is cancelled, therefore lambda 1 is equal to lambda 2, lambda 1 is given lambda, therefore lambda 2 is also lambda. Now next, that is asked in 2019. A metal plate of area 10⁻² minus 4 meters square is illuminated by a radiation of 16 milliwatt per meter square. Here also the intensity is given. The work function of the metal is 5 electron volt. The energy of the incident photon is 10 electron volt, and only 10% of it produces the photoelectrons. The number of emitted photoelectrons per second and their maximum energy respectively will be. That means we have to find out the number of the photoelectrons emitted per second, and also what should be the maximum energy of this emitted photoelectrons. Now for that purpose we know that the intensity I is equal to energy per unit area unit time. Therefore total energy E is equal to IA. I is given 16 milliwatt per meter square, right? Therefore 16 into 10⁻² minus, area is given 10⁻² minus 4 and 1 second, therefore 16 into 10⁻² minus 7 joule. That much energy is incident. Out of this, only 10% energy produce the photoelectrons. Therefore, EDS is equal to 10% of. So it's equal to 16 into 10⁻² minus 7 into 10 upon 100. Is equal to 16 into 10⁻² minus 8 joule. So this energy can produce the photoelectrons. Therefore, the number of electrons emitted, therefore, numbers of electrons emitted is equal to N is equal to EDS upon E. Therefore, 16 into 10⁻² minus 7 minus 8 upon 10 into 1.6 into 10⁻² minus 90. That is given in electron volt energy. We convert into the joule because EDS is also in joule. Therefore, 10⁻11 photons per second are produced. Photons per second. Now, what should be the maximum energy? Maximum energy is HF minus HF0, that means the 10 electron volt minus 5 electron volt, that means the 5 electron volt is the maximum energy of these emitted photons. So here intensity is given. First we find out what is the total energy incident on the surface. So total energy incident is E is equal to IAT. So we obtain the E is equal to 16 into 10⁻² minus 7 joule. Now, out of this incident energy, only 10% energy produce the photoelectron. Therefore, the EDS is the 10% of E. We obtain the 16 into 10⁻² minus 8 joule. Now, the numbers of the electrons emitted is N is equal to EDS upon E, 10% of energy upon total energy. So we obtain the 10⁻11. Now, what should be the maximum energy of this photoelectrons emitted? Therefore, HF minus HF0, 10 electron volt minus 5 electron volt. Therefore, 5 electron volt is the energy, maximum energy of the photoelectrons are emitted. Clear this? Okay. Okay, after the discussion of the MCQ question asked in JEE, Now, after that, we consider the MCQ question asked in all India PMT and also Neet exam. Now, we take the first exam, first MCQ asked in 1994. Work function of metal in photoelectric effect is 3.5 electron volt is given. For minus 1.2 volt potential, photoelectric current becomes zero. Hence, which of the following sentence is right? Again here, the work function of a metal in photoelectric effect is given 3.5 electron volt. As we apply the potential difference of minus 1.2 volt, the photoelectric current becomes zero. Actually, there is the stopping potential. We apply this type of the negative voltage, so photoelectric current becomes the zero. Therefore, the no any photoelectron reaches to the collector. So in this case, which sentence is right? First is the energy of the incident photon is 4.7 electron volt. Second, energy of the incident photon is 2.3 electron volt. Third, when the photon of the high frequency are used, the photoelectric current will be produced. And third is when the energy of the photon 2.3 electron volt, then the photoelectric current is maximum. Okay? For that purpose, we are using the concept the energy of the incident photon from the equation E is equal to HF minus phi. HF minus phi. Therefore, HF is equal to E plus phi. E plus phi. Therefore, as we find out the energy of the incident photon, so we can judge it. Right? Therefore, the E plus phi is given HF is equal to 3.5 plus work function is 1.2. Work function is 3.5 and potential is this. Okay. Therefore, the 4.7 electron volt is the energy of incident photon. Thus, the energy of the incident photon is 4.7 electron volt. Again, here the work function is given phi and stopping potential is given minus 1.2 volt. So, in this case, the current becomes the zero. What should be the following option is there? The energy of the incident photon is 4.7 electron volt because we are using this equation E is equal to HF minus phi. Therefore, HF is equal to E plus phi. E is the applied potential. So that is the 1.2 and HF is 3.5. Therefore, 4.7 electron volt. Now after that, the next question asked in 1995, when the electrons with the mass m is accelerated with the d volt, associated de Broglie wavelength is lambda. Now when the proton with the mass capital M is accelerated with the same potential, so what is the de Broglie wavelength for this proton? Now we know that the de Broglie wavelength lambda is equal to H upon under root of 2m qv. 2m q. Now the charge of the proton and electron are same. Accelerated voltage are same. H is the constant. From this equation, lambda proportional to the 1 upon under root of m. 1 upon under root of m. Therefore, the de Broglie wavelength of proton to the de Broglie wavelength of electron is equal to under root of me upon mg. Mass of the electron to the mass of the proton. Mass of the electron is given the small m. Mass of the proton is given the capital M. Therefore, under root of small m upon capital M. And wavelength of electron is given the lambda. Therefore, wavelength of proton is equal to wavelength of electron into ratio of mass of electron to the mass of proton. Again, when the electron with mass small m is accelerated by the voltage capital M, associated de Broglie wavelength is lambda. Now, when the proton with mass capital N is accelerated with the same potential difference capital V, then the associated de Broglie wavelength of proton will be. For that purpose, we know that the de Broglie wavelength for accelerating voltage V, the equation lambda is equal to h upon under root of 2m qv. K is the charge, V is the accelerated voltage, m is the mass of the particle. Okay. So here the accelerated voltage for the electron and proton are same, charge are same, therefore lambda proportional to the 1 upon under root of m. For that purpose, the lambda E upon lambda E is equal to under root of me upon mt. But the associated de Broglie wavelength for electron is given lambda. Therefore, we can write lambda P is equal to lambda under root of small m upon capital M. Clear? Okay. Now next is for wave concerned with proton. The de Broglie wavelength changes by 0.25%. If its momentum changes by P0, so initial momentum of the proton is, what is the initial momentum? For that purpose, we know that lambda is equal to h upon p. As momentum increases, as p increases, lambda decreases. Lambda decreases. Now the lambda is increased, changed by the 0.25%. Therefore, lambda plus 0.25 upon 100 lambda is equal to change in momentum is h upon p minus p0. Here the lambda increases, so p decreases. Right? So that is our equation 1 and that is 2. Taking ratio of equation 2 to 1. Therefore, we can write 100.25 lambda upon 100 is equal to P upon P minus P0. Lambda is cancelled already by taking the ratio. Here we simplified left hand side, therefore there is the 100.25 lambda upon 100. That is the equation number 2. Because here we take the simply LCM is the 100, so 100 lambda plus 0.25 lambda upon 100. Right? Therefore lambda is common, 100.25 lambda upon 100. That is the simplification. So by simplifying this, we obtain the P is equal to 100.25 upon 0.25 P0. Therefore, 401 P0. So the initial momentum of the proton is 401 P0. Again, by using the concept that the Broglie wavelength is equal to h upon p. From this equation, as the p increases, lambda decreases, or the lambda increases, p decreases. Here the lambda increased by the 0.25%, therefore lambda plus 0.25 lambda is equal to h upon p minus p0. Let me simplify this, so 100.25 lambda upon 100, but now taking the ratio of equation 2 to 1. Equation 2 to 1. Therefore, 100.25 upon 100 is equal to P upon P minus P0. If we simplify it, we obtain the P is equal to 100.25 upon 0.25 P0, that means the 401 P0. 401 P0. Now after that, the question asked in 2003, the photocell is kept at 1 meter distance from the source. Now the distance from the source is changed to 2 meters. Then, which option is that? Number of the photoelectrons emitted are 1/4 times the initial value. That means the number of photons emitted is decreases by 1 by 4 times. Second, energy of the electron emitted is 1 by 4 times initial energy. That means the energy of the emitted photoelectrons is increased by 1 by 4 times of initial energy. Next, numbers of the electrons emitted is half of the initial electron emitted. It shows that the numbers of the electrons emitted becomes the half of the initial. And next is energy of the electrons emitted is half of the initial energy. Now the energy becomes the half as the distance becomes the double. Now what is the result? Now the power is equal to number of photon emitted. Power P is directly proportional to the number of photoelectrons. That is capital. And power P is directly proportional to the 1 upon R squared. Therefore, number of electron is also depends on, but the numbers of the photoelectrons emitted is proportional to the, inversely proportional to the R squared. Distance is increased by 2 meters. Therefore, 1 upon 2 squared, therefore 1 upon 4 times decreases. Numbers of the photoelectrons emitted are 1 by 4 times of initial value. That is our right answer. According to this relation, and because the power is directly proportional to the photoelectrons emitted. Now the power is directly proportional to the 1 upon R square. Therefore, number of photoelectrons emitted is also directly proportional to the 1 upon R square. Clear? Now next, momentum of photon being 1 MeV, having the 1 MeV energy is how much kg meter per second. Now we know that the first the 1 MeV energy is equal to what? 1.6 10 is to minus 19 into 10 is to 6. Therefore, 1.6 into 10 is to minus 13 joules. Now we know that momentum of electrons P is equal to E by C. P is equal to E by C. That means the 1.6 into 10 is to minus 13 upon 3 into 10 is to 8. That is the velocity of light in vacuum. Therefore, we obtain 5 into 10 is to minus 22 kg meter per second. Where is the numerical? Here the momentum of photon having the 1 MeV energy is given. So what should be the momentum of the photoelectrons? So 1 MeV energy is given, it means the 1.6 into 10 is to minus 19 joule, that is the corresponding to the 1 electron volt. But here the mega electron volt is given, so again multiply the 10 is to 6. Therefore 1.6 into 10 is to minus 13 joule. Now momentum of photon P is equal to E by C. E already we have 1.6 into 10 is to minus 13 joule. C is the velocity of light in vacuum, 3 into 10 is to 8. Therefore 5 into 10 is to minus 22 kg meter per second is the momentum. So momentum of photon associated with 1 MeV energy. Okay? Okay.